Good morning, everyone. My name is Brian Phipps. I'm one of the engineers here at Minoxavent, and welcome to another chapter in our webinar series. Today's presentation is going to be given by Mike Murphy. I'm sure many of you are familiar with him. He's our National Sales Manager. He's been with us since 2009, has a BS degree in Business Administration. He's responsible for maintaining and growing the global representative network and certainly does his best to get around to as many of your offices and people as possible. The presentation he's going to give today is source capture system design. He's going to go a little bit into just not only the basics of our products, but also how we can offer design services for things that are not always cut and dry and plan and spec work. Now, without further ado, I'm going to go ahead and turn it over to Mike.
Well, thank you very much, Brian, and good morning, everyone. The idea behind this webinar is really just to discuss some very simple design practices. We're going to start a foundation, and then we'll get into more detail in future webinars. Okay, the first one is we have many resources to discuss why we need source capture. This particular one is from the Industrial Ventilation Guide, and it just states the object of providing ventilation for vehicles in an environment to keep the workers' exposure to toxic exhaust down. The bottom line is we want to protect the breathing zone of the worker. And generally speaking, it's less expensive to capture the contaminant at its source and remove it as opposed to doing complete room air exchanges. Here's another resource. This one is from NIOSH, the National Institute for Occupational Safety and Health, and it also talks about source capture. In particular, the first sentence I think is very important. It says several studies over the past 5 years indicate that workers exposed to diesel exhaust over a number of years are more likely to contract lung cancer. Now, obviously, we want to do everything we can to prevent that from happening. Another resource is OSHA. It talks about specific levels. This is a resource, and again, this is from the IMC, or the International Mechanical Code, but there's some very important information in here as well. So you can read it at a later date, but a couple of things I'd like to point out. In the first paragraph, it says, in motor vehicle repair areas, an exhaust system shall be provided to connect directly to the motor vehicle exhaust. And then below that, source capture system, a mechanical exhaust system to design and constructed to capture air contaminants to exhaust such contaminants to the outdoors. Again, the whole goal of this is to make sure that we're preventing breathing zones from being contaminated. Be sure to check, these are national or federal codes, be sure to check all your local codes as well to make sure that you're in compliance. So some simple key terms. The first one is CFM, cubic feet per minute. Really, that's the volume of air that we are moving. So that helps us, that's a design criteria that we need to know in order to properly design a system. Next would be static pressure. In the definition, it says total pressure to a given point in a system. Basically, we're moving air through the ductwork, and that creates resistance called static pressure. We want to make sure that we know the static pressure because those are design criteria when we're designing our fans and our systems. Next would be the FPM, which is feet per minute. This is a measure of airspeed that is expressed by feet per minute in ductwork and allows us to design the capture velocity. Now, sometimes it's called transport velocity or conveying velocity, but the idea behind that is we want to have enough conveying velocity that allows us to keep the particulate in the airstream and then deposit it where we want it deposited. And then the last one is RPM, or revolution per minute. Basically, that's the speed of the fan, and again, that is part of our design criteria for designing a source capture system. Now, these are some very simple guidelines, and please note that these are for normal tune-up or idling type applications. There are many other applications like dynamometers and maybe heavy hydraulic testing or pump testing, but the criteria that I'm talking about today is for normal tune-up and idling type applications. So for cars and light trucks in an idling or tune-up type application, we recommend 300 CFM at 4 inches of static pressure. Next is medium trucks and light buses, 450 CFM at 5 inches. I'm sorry, when I said for 300 CFM, that's 4-inch diameter hose will allow us to get the 300 CFM at the correct conveying velocity. For medium trucks and light buses, 450 CFM at 5-inch diameter hose. And then for larger vehicles, buses, trucks, some agricultural equipment, some industrial equipment. We want to be 600 CFM at 6-inch diameter hose. And again, we want to size the ductwork for approximately 2,000 to 2,500 feet per minute. Reason for that is that's what it's going to take to allow that particulate to stay in the airstream. Again, we don't want anything falling out of the airstream. All right, so recommended hose types. Now, bottom line for this, I talk about our 5000 series or our 4000 series hose, and that's the Minoxavent hose. But to keep general, you want a hose that can handle about 350 degrees continuous and up to 550 degrees intermittent for cars and light trucks and tune-up applications. And then for the larger vehicles, the semi-trucks, the diesel buses, things like that, we want to use a hose that can handle 600 degrees continuous and up to 1250 degrees intermittent. One thing that I always tell the engineers when I'm doing a presentation for them is it's very important when you write your specification to include the word continuous if that's what you want. And the reason for that is this. If Minoxavent sees a specification or a system design that calls out 600 degree hose, we're going to assume you meant continuous, and that's how we'll quote the system. But some of our competitors, unfortunately, will see 600 degrees, and for whatever reason, they'll assume that you meant intermittent, which I know isn't logical, but that does occur. And what happens then is they may win the bid because that hose would be a less temperature rated hose and it would be less expensive. The problem is your customer won't get the hose that they need for that application. So just by adding the word continuous, you're more likely to get what your design desires. This is another resource here. This is from the American Conference of Governmental Industrial Hygienists. And this chart can be used for specific CFM requirements when designing a system. So you can see there's 4 specific vehicles on that particular chart. I think the next sheet is a little bit more informative. Basically, this is one that Minoxavent has put together. And I guess first let's look at the definitions. So on the bottom right, we've defined no load as vehicle is running for short periods without hydraulic or dyno. Light load, engine is revving for longer period of times for tune-up type applications. Full load is for dyno applications or hydraulic testing. For those types of applications, you want to work directly with us because there's going to be some extra design criteria that we need to take a look at. So let's just take an example. If we look at the 4-cycle diesel with turbo and we look at 800 cubic inch engine, so let's look at the RPM at 750. If you look all the way over for full load, that requires 370 CFM. Now take a look at the same engine but revved up to 2100 and look at the full load. You're up to 3,330 CFM. And the reason I'm pointing that out to you, you note the difference there. That's to state this, that in fact, it's not necessarily the vehicle, it's how the vehicle is being run. And we always want to size our systems around the worst case scenarios, right? So if 90% of the time you're only running at idle, but that 10% of the time you're running at high rev, well, that's how we have to size the equipment to make sure that we're set to handle worst case scenarios. One note on this sheet, 2-cycle engine, you double that because it fires twice as many times as a 4-cycle engine. So just to give you a little heads up on that. Next is a CFM calculation sheet that we offer, and basically this allows you to fill in the needed information to calculate your CFM requirements. And again, so note that this is not based on horsepower. Often we're giving horsepowers of vehicles and ask to design a system. That's not enough information. We need to know, and we need to put into this equation the cubic inch, the exhaust temp, and the RPM. How is the engine going to be running? So to help facilitate that, we have what we call our design worksheet. Basically, this is designed to ask the questions that you or I or we will need answers to properly size a system. So very quickly, you can see whether it's private passenger vehicles or commercial vehicles. We need to know the type of vehicles. Is there a dynamometer? Are they natural gas? Is there a turbo? Basically, the most important, I mean, all of it should be filled up, but most important is the engine data, the cubic inch of displacement or liter, and the RPM. How is it going to be run in a particular application? And then the second
Thanks,
page,
Mike.
this is all.
Cut you off there right quick. We've had a couple of questions come in. First off, when you're talking about the CFM calculations on that spreadsheet a couple slides ago, are you looking at exhaust temperature, your exhaust in there at exhaust temperature, or are you using standard air temperature when you're calculating those CFM?
Exhaust temperature.
Okay. And another question, the required CFMs that we're showing, are we just putting the CFM that's coming out of the exhaust pipe, or are our systems pulling in more air than is actually coming out?
Well, we like to size it with 15 to 20% of ambient air, and that just helps make sure there's no leakage around the tailpipe, but it also helps cool the exhaust as it goes through the equipment. So the slide that's in front of us now is just the second page to that design worksheet. Basically what that does is, if you have an idea, maybe it's a blueprint for a new building or an existing building, what the layout is, what we need to look at in order to make some design choices of the equipment that we're going to put into place. Okay, hose determination. So this is, whether it's a hose reel or an overhead system, basically hose. How long do we need? Well, there's a couple of different things to think about. By specification, meaning if the engineer has already decided the length of hose, that number will be identified in there, or by triangulation, and I'll show you a slide on that to mathematically figure out the length of hose that we need. So my next one, and I'd love to say this, is how much hose can a hose reel hold? And really, that's based on the diameter of hose and the particular hose reel itself. When we look at that, we size a hose reel, or we pick a hose reel, so that the hose can be completely wrapped around the drum. So that's how we pick it. And we have many different sizes of hose reels to make sure that it can handle for that application. Is hose weight a factor? Well, it certainly is. There are different types of hoses. Those hoses have different weight capacities. And then the hose reels themselves, the spring cassette, have different weight capacities. So luckily we have a big selection and we can pick a hose reel to fit into that category. But yes, hose weight does play a role in system design. What determines hose type? Well, certainly exhaust temperature. We run from 350 degrees all the way up to 2,000 degrees. So we have to make sure that we pick the right hose for that particular application. Chemical resistance plays a role in the type of hose that we'll use, and also abrasion resistance. So if this is on a hose reel and it's going to be above the ground all the time, that would be one set of circumstances. But if it's going to be dragged across the floor, or it's going to be drug over sharp tool kits and things like that, well, then we're going to want a different type of hose for those applications. What determines hose diameter? Well, we already talked a little bit about that, but certainly the vehicle type, the air volume, and the desired velocity and pressure drops that we need to, again, we want to keep that particulate in the air and convey it to where we want it to be conveyed to. Now, what type of hose should not be used on a hose reel or even an overhead system? No crush, certainly, because it would collapse on the drum. Metal hose, you can't use a metal hose on a hose reel because it doesn't have the bending radius. So let's just talk about an overhead system. You could use no crush hose on the lowest section of an overhead system if in fact it's going to be drug on the ground. You could even do that on a hose reel as long as it's the end of it and it's not going to be wrapped around the drum. Metal hose, technically you could use metal hose on an overhead system, certainly not on a hose reel, but it's not recommended because, again, it just doesn't have a very good bending radius. All right, so this is a sheet that helps you determine the length of hose that you'll need for a given application. And basically, it's a mathematical equation. C equals the square root of A squared plus B squared. So if you take a look at that equation and you see finally the end result is we need 17.21 feet of hose, well, then we would recommend a standard length of 24 feet of hose to be able to properly cover that, that bay or that vehicle or that application. All right, a typical hose reel package consists of, and again, this isn't just for hose reels, but this is for overhead systems as well. So you'd either have the hose reel itself, or for an overhead system, it would come with the balancer and bracketry and things like that. Certainly the hose, the tailpipe adapter. Things to consider, we want to make sure that obviously it's got to work. In most instances, it has to work with a fan. You could have a fan on-off switch. It could be remote or on the reel. Fan controls. Diesel canes, quick disconnects for hoses and nozzle assemblies where maybe you want to quickly disconnect from a vertical stack to a below chassis tailpipe, and Y assemblies. The Y kit assemblies are great for dual exhaust vehicles. All right, this is a picture showing, and I guess my thought process on this would be, if I'm designing a system, if it's an existing building, I would like to take a look and see exactly what's around the area that I want to handle with vehicle exhaust. And if it's a new building, I want to make sure by looking at the prints, what kind of obstacles will I see? This picture is good because it shows hose reels but it also shows an overhead crane. And if you look at this picture, it looks like that crane is going to come right towards those hose reels. So for this application, we utilized motorized hose reels because we can get that hose completely up out of the way of the crane so the crane can travel back and forth. And then another application would be a pack arm with a drop on it. And basically, if you look at that, we've stayed underneath the crane. We've used a pack so we can move this in and out as we need to. And then notice the ductwork is back and along the wall. So we are completely out of the way of the overhead crane. Next is an underground exhaust system. Basically, what I wanted to talk about here very briefly is we'll show you some pictures of how an underground system works. But as far as design criteria, we have, let's say, a 3-inch or 4-inch hose going into ductwork in the ground. We need the minimum diameter of that ductwork to be 8-inch, because remember that 3-inch or 4-inch hose is going to take up a lot of that open area of the duct. And then for 5-inch or 6-inch, we want to make sure that we have a 10-inch minimum diameter of duct, again for the same reason, so we get our proper air flow or air volume. Now, an in-ground system is very nice. You can see how neat and clean it is. The design is the hose is stored inside that area. So this really kind of demonstrates what I'm talking about, to making sure that we have enough open air space in our ductwork so that we can properly size the system. Some components for designing an in-ground system. Well, certainly we have the outlet assembly. We have the hose. Normally for this we use our 3000 series no crush type hose. A nozzle. Normally the rubber nozzle, and then the hose guide to help guide the hose back into the ductwork. Now this is very important. When designing an underground system, we recommend that you use our Underduct VE. Underduct VE is a fiberglass reinforced plastic ductwork. It can handle the 325-degree temperature range that we typically see for vehicle exhaust. The benefit of this is that it's not going to be negatively impacted by the corrosive nature of the earth, so that ductwork will be there probably long after the building is even there. And secondly, you get better air efficiencies because of the smooth ID. One of the things I'd like to point out for this, particularly for the VE Underduct, the Underduct VE is the only non-metallic vehicle exhaust duct certified to meet building codes by the International Code Council. So again, that helps set us apart from all of our competitors. Now for rail systems, a rail system is a great way to have a lot of flexibility and minimize the number of drops we need to handle that particular area. So a couple of things to think about when designing a rail system. The Techno Rail, it can do up to 3,000 CFM, so basically it's 600 CFM drops for a Techno Rail system. That would be perfect, again, for cars all the way up to buses. The ALU 150, it's a little bit larger than the Techno Rail, so it can do up to 4,000 CFM. And again, that's very similar, 600 CFM drops. And then the ALU 250, depending on the length, it can do up to 7,000 CFM. We could do 800 CFM drops, so it's for larger applications. A couple of things to think about when designing a rail system. 8 inches of static pressure or less. That's what we recommend, to make sure we're not sucking the lips together so the trolley can travel back and forth easily. Anything over 8 inch, if you think your system is going to be designed with more than 8 inches static pressure, please contact us. A couple of things to think about again would be, so the trolley itself, it's about 3.5 inches of static pressure. The hose reel, that's going to add, or it will add about a 1/2 inch, so it's going to be a total of 4 inches of static pressure. And then it's about a 1/2 inch of static pressure per 100 foot of rail. So just things to think about when we're designing a rail type system. Now next, I'm showing you a picture of a door port. This is just because there are very simple systems still in practice today. So if you're designing a very simple system, maybe like what we show here, you can see this is kind of old school Minoxidant, but we still sell this product today. We've been around since 1953, so we do it very well. What we're showing here basically is a tailpipe. So you have a tailpipe adapter on the tailpipe, you have the hose, you have the door port. And this is all under positive pressure. So it's the car or the engine and expelling positive pressure into the hose environment, and that's being carried to the outside. The ideal situation for that is keep the hose short and straight as possible. Now this picture is showing a metal hose. Again, we would recommend using our no crush hose just in case it gets run over. So with that being said, that's it for vehicle exhaust. I'm going to move on to some simple welding source capture criteria. System sizing guidelines for welding and fume applications. So for standard welding, usually at 6-inch diameter arms, we need 600, 700 CFM. for maybe we're typically welding on very lubricated material, maybe it's a pre-lube material, and it generates, as it heats up, it generates a lot of smoke and exhaust. We may want to use an 8-inch diameter hose, and in that case we'd size it for 1,000 to 1,200 CFM. And again, we need the same type of conveying velocity, 2,000 to 2,500 feet per minute. Again, the idea is just to keep that particulate moving through our ductwork. All right, next we have our welding arms. This is an internally supported arm. So when I say internally supported, what that means is that the support structure is internal to the hose environment. And then we have an externally supported arm. And that is the support structure is external to the hose environment. There's different applications, different pricing structures. One thing to think about maybe is depending on the environment and what we're doing. So if we're in a really dirty, dingy, greasy environment, we may want to use an internally supported arm to kind of protect that structure. On the other hand, if maybe the exhaust that we're doing is very, maybe it's corrosive or just nasty exhaust, then we would probably want to use an externally supported arm. And we also get better air efficiencies with the externally supported arm because there's no obstruction to the internal hose environment. All right, then mini arms. These can be wall mounted, ceiling mounted, or desktop mounted. They come from 1-inch to 4-inch diameter, and there's different material depending on the application. So when you're designing a system, get a good feel for what the application is. So an example would be a couple of years ago we did a big job in Michigan, and they were soldering on some very sophisticated circuitry board, and they could not afford to have a static electricity discharge. It would negatively impact the components. So in those cases, they used an arm that was constructed of a carbon-based material, which prevented the buildup and thus the discharge of static electricity. So just an idea, we just want to make sure we know when we're designing these types of systems, what is the environment, what is the fume or particulate that we're capturing. Slotted fume hoods. So we size these for 350 CFM per foot of hood. We size the slots for 2,000 feet per minute capture velocity. The best capture capability is if we stay within 18 to 24 inches of the source. We want to keep that within as close to the slot, again, 18 to 24 inches from the slot to the source of the contaminant. And we want to protect the airstream as best we can. So if the situation allows, side skirts are a nice way to prevent turbulent air moving back and forth and changing the path of the exhaust. If the situation allows, that's a nice way to protect it. The more protected the exhaust is, the easier it is to capture. All right, some hood design information. These apply not only to slotted hoods, but they're for canopy hoods as well. I guess the most important information on this page is elimination of sources of air motion as a first step in hood design is an important factor in cutting down the required air volume. So you get an idea there. This talks about thermal air currents, material motion, even movement of the operator. Another thing to think about where I've seen, we're trying to capture welding exhaust, and there's a man fan there, and it's constantly blowing against the exhaust that's being created, and then it's difficult to capture that exhaust. So just be cognizant of what's around you, what's creating air turbulence, so that we give ourselves the best chance of capturing the particular exhaust. All right, hood design data. Basically, this is just talking about capture velocity, and it gives you kind of a range. So from very simple evaporation from tanks, things like that, 50 to 100 capture velocity, or 50 to 100 feet per minute. But then if you look down to grinding, abrasive blasting, and tubbling, it can be all the way up to 2,000, maybe even 2,500 feet per minute. So it's just very important when designing a system that we know what our obstacles are. All right, range of design flexibility. So we need to keep the particulate in the airstream. I've said that 100 times, but that's very important. You know, if you look at some of these, when I first looked at it, I thought, well, certainly fumes, zinc and aluminum oxide fumes can't be that much different than maybe the particulate in welding exhaust or fume exhaust, and this is 1,400 to 2,000, where we recommend 2,000 to 2,500 feet per minute. But basically, the reason that we do that is we want to keep the ductwork as small as possible, and we want to limit the pressure drop that we create. So we found that the 2,000 to 2,500 feet per minute range works best when designing systems for this type of capture. All right,
Hey,
this
Mike,
is
let me
a
interrupt you again quick for another question. Just backing up a little bit to the slotted fume hoods, you mentioned that we can add side skirts on there to protect them from any sort of cross breeze, interrupting the airflow, pulling fumes away from the breathing zone. What if we have a customer that, 90% of the time they're able to use the side skirts, but once in a while they bring something in the welding booth that just doesn't fit in there? Are they going to have to, take a lot of time to remove the side skirts, or what sort of options do we offer for that?
well, we can hinge the side skirts so they very easily can be moved out of the way when we don't need them and moved back into position when we do. So that's a very easy obstacle to overcome. You're welcome. Okay, so next we're talking about the SMACNA round negative pressure duct chart. This is available to everyone, but basically, just so you know how we do it, we use the negative 10 inches for our welding and vehicle exhaust. That's where we're most comfortable when we're designing duct work. If you need higher negative pressure, maybe for abrasive applications, you can refer to the SMACNA Industrial Duct Construction Standard. All right, then we'll talk a little bit about fans. So this is our fan. We make these fans right in Rock Island. They're direct drive. They go from 0.5 horsepower to 3 horsepower. Here's a typical curve of our fans. For these particular fans, kind of the sweet spot is from 3-inch to 6-inch static pressure range. These work very effectively in those ranges. Now for the larger fans, we have the belt drive, backward incline, centrifugal vent set. Now this particular curve shows, in this curve, the 1700 to 2000 CF range is the sweet spot. So if you're looking at it and you're designing a system, you want to stay in that sweet spot. If you get into the area where the boxes don't have numbers in them, that's the unstable part of the curve. You want to stay out of that area when you're designing a system. All right, so source capture fans and VFDs and how they affect each other. More and more recently, we get asked about adding VFDs to our system. So certainly that's up to the engineer specifying, designing the project. Bottom line, for me personally, if you're doing 1 or 2 or maybe even up to 5 hose reels, that seems to be a bit of a waste of time. It would be difficult to regain the payback on that. For beyond that, maybe 8, 10, then maybe it's worth it. So, but some things to think about. Historically, if you're putting a VFD on a fan, you're going to use a static pressure sensor, and the fan will then ramp up or down depending on how many drops are open or closed. So the more drops that are open, the static pressure drops and the fan speeds up. The more drops that are closed, the static pressure goes down and the fan slows down. So with that being said, is a difficult design criteria that has to be met. You need to find a fan that can work that range. So in this example, this is a BI 180. It's an 18-inch wheel, and we're talking about a 5-inch static pressure. So in this particular case, at 5 inches, the range is 4,200 to 3,600 CFM. That's basically a 600 CFM difference. A VFD would not be a practical addition in this particular application, or this fan would not work for a VFD system. Here's another bad example of that as well. So this is a BI 195, so it's a 19.5-inch wheel. And if you look at that at 5 inches of static, we're at 4950 to 4250, so basically 700 CFM difference. So again, this would not be a good pick for that type of a system. Now here is we call this the 110 MHA, or material handling. Basically, this is a 19-inch wheel. If you look at the range there at 5 inches, it can do 7,800 to 1,600 CFM at 5 inches of static pressure. So this would be an appropriate selection to use with a VFD in this particular system design. The key in this is to make sure that the fan performance, the range, and the duct layout and sizing all comes together to give you your best chance of success. Now we're moving on to collection, dust collection. Not every application lends itself to source capture, so we do offer general ventilation in those situations. This particular one is what we call the racetrack pattern. This is good for smaller spaces, and it's kind of chasing the air around. So you're capturing everything up at the ceiling height or above certainly the work zone that makes its way up there. The problem with this is that it's not catching all the particulate, because all the particulate doesn't make it up to this capture area. So it's certainly better than nothing, but not as good as a source capture system. And this is another type of system. This is for larger air spaces. They call this the shuttle air pattern. Again, we're pushing and pulling dirty air. We're cleaning it. We're moving it across. So another design system for applications where you just can't use direct source capture. Now, this is another resource for you, and this is the air exchange rates. So there's a lot of information on here, but I'll just pick one as an example, and that's if you look down and you see welding. They talk for welding, it's 4 to 8 minutes for air exchange rate. So what you do basically, there's an equation where you take the length times the width times the height of the space. You divide it by the air exchange rate, and that equals the total CFM required. And once you have the total CFM required, then you can kind of get an idea of what the unit capacity that you're thinking about using is. And then you take your total CFM required divided by the unit capacity, and that tells you how many units you will need to add to your specific design. Now, these are our round tables. Typically, the capture velocity is 150 to 200 feet per minute. Basically, you take your table size times your capture velocity. So in the case of the bottom right, you have a 3-foot wide table by 2 foot deep equals 6 inch times your 200 feet per minute capture velocity. You're going to be at 1,200 for that particular unit. With that being said, there's three units shown up here. The red and the blue are self-contained. So if you're designing a system and maybe you want a self-contained system, those are great ways to do it. They have the fan and they have the cartridge built right into the system. And then the one at the bottom right is ducted. So if you look behind it, you can see the duct work, and that's being captured and then in this particular case sent right over to a dust collection system. All right, so things to ask when you're designing a dust collection system. Total CFM. What do we need for total CFM? What is the static pressure? Because that's what we're going to use for designing our fan. What is the dust? What is the volume of dust? Is there temperature concerns? What is the temperature of the dust? Is it explosive? Is it flammable? Do you want the collector to go inside or outside? You know, it may take up it will take up a specific footprint. It may take up larger or more room than you have inside and you want to move it outside. We'll need to know that. And then what is the expectation of the system? Do you want this system just to get the majority of the dust, or do you want this system so clean that you can eat off the floor? So those are things to think about when you're designing a dust collection system. Now, application data sheet. Similar to the design worksheet for vehicle exhaust, we have design sheets for different applications. This particular one is designed for cyclone. So if we're designing a system, a cyclone system, we'll want to have this page and this page filled out in its entirety, if possible, to give us the best chance for doing a good design for that application. This application data sheet is for mist collectors or mist eliminators. This particular one is for buffing and polishing. So you get the idea. There's different criteria for different applications in order to give us the best chance of being successful. This one is powder coating. And then the last one, this is for metal and woodworking application. So we need you to be as specific as possible. It's not enough just to say, well, I have a sander and I have a grinder. We need to know specific information. For example, how wide is the wheel on the grinder? How wide is the belt on the sander? Because you could look at the chart and you can see how the details of the different tools play a role in the design of this particular solution for that type of an application. A quick example would be, there's our division manager, Eric Swanson, went in an application one time where the customer was complaining that the dust collection wasn't working properly. What he found was there was a 36-inch wide belt sander, and that typically requires 1,600 CFM just for that. And then there were other tools as well, but the total system design was for 900 CFM. So there was no way that had a chance of being successful in that particular application. Now, with all that being said, I created a cheat sheet that I thought you might have interest in. Basically, this is general system sizing guidelines for normal tune-up and idling type applications, and then general system sizing guidelines for welding and fube applications. So this will give you the foundation to begin your design processes. With that being said, I want to thank you very much for your time. It's greatly appreciated, and I'll go ahead and turn it back over to Brian.
All righty, thank you, Mike, and a big thank you to all our attendees today. We do appreciate the time you take to join us on these Friday mornings. Now, if you have any questions we didn't get to, if you'd like a copy of this presentation, we do publish and put them all on our YouTube channel. That can be found by going to www.minoxevent.com, click on the Media Center tab, and click Webinars. Now, if you'd like a hard copy of it, like a PowerPoint presentation or any of our previous webinars, be sure to give us a call, give us an email. Again, any questions we didn't get answered, or especially if you have any suggestions for any future webinars we do. We certainly put these on so that you, our audience, can get beneficial information from them, so we do appreciate any constructive criticism you can give us on those. Next month's webinar will be the last Friday, 10 a.m. as usual, and we're going to be having that on our fiberglass reinforced plastic products. Again, thanks for your time, and have a great weekend.